So good morning, everybody. My name is Lucie Mathieu. I'm an associate professor at the University of Quebec in Chicoutimi, here in Saguenay. And today I'm going to talk about what we've done along the Shibugamo Transect. This project has been has ended a few months ago, and we are wrapping up the last papers at the moment. And I'm also going to refer to the few thematic projects that we've carried here in Chicoutimi. So as an introduction, the Shibugamo area is located in the northeastern corner of the Abitibi greenstone belt in the southern part of the Superior Plateau. And this area is very interesting because it's different from the rest of the Abitibi. So what we realized early on in the project is that it was different from a structural point of view on the metallogenic point of view, and that it's actually the northern part of the Abitibi greenstone belt that is called the Matagami-Shibugamo greenstone belt that evolves differently from the rest of the Abitibi subprovince. So this is a general context, and it was an ideal area to look at in details and to compare to the southern part of the Abitibi to see what are the main constraints, what leads to efficient gold mineralization, like orogenic gold deposit, like we see in the south, compared to the Shibugamo area where magmatic hydrothermal style of mineralization is much more common. So this is mostly what I'm going to talk about. I'm going to refer a lot to the magmatic activity because this is what we focus on in Chicoutimi. So if I summarize, you have the summary of the ages here on this slide. I like to view the evolution of greenstone belt as in two main stages, the synvolcanic and the syntectonic stage. I know it doesn't make much sense from a structural point of view, but from a magmatic point of view, it makes a lot of sense. Why do I say that? That if you look at this classification by Jean-François Moyen, here we really have two types of intermediate to felsic intrusive and magmatic activity, in greenstone belt. You've got the TTG during the main phase of construction of your belt when there is most of the magmatic activity, and then you've got potassium-richer magma, and the diversity of magma, you've got biotite granite, sanigitoid, alkaline in series, etc., etc. So there's really two stages in at least that we see in the intermediate to felsic magmatism, and these are the two stages I'm referring to here, the synvolcanic and the syntectonic stage. You see that on this compilation by Oscar Laurent in 2014 here, a long stage of TTG magmatism, that's the synvolcanic stage. That's when you have most of the basalt lava flow also forming central volcano, etc., which is followed by a short period of deformation, sedimentation, and potassium-rich magmatism. So for the Abitibi greenstone belt, we know in the north it's a bit older than in the rest of the sub-province. In the Shibugamo area, we have 2.8 giga-years old intrusions and volcanic units, which are also very old, and it goes up to 2.700 giga-years on average. And in the south, you've got the same events, but a bit younger. So looking at magmatic system, there is a specific type of metallogenic model we are investigating when we do that. We look mostly at porphyry style of mineralization. This would be associated mostly with intrusive system of the synvolcanic stage. And we also look at intrusion-related gold system, which will mostly be related to intrusion of the syntectonic stage. So let me give you an overview of what we've done so far. There is a lot of work that has been carried around the Shibugamo Transect, and that included trying to understand the magmatic system better. I'm going to talk about that in the next slides, but it also involved details on the structure of the area, using the seismic geophysical data, but also mapping, also a structural investigation by Pierre Bedeau, and it also implied more details on the geochronology, detail mapping, etc., etc. So really, we took all of this data and were able to comment on the geodynamic evolution of this part of the greenstone belt and how this relates to the mineralizing systems. So here you've got, again, a summary of all this. In the top left corner, that's the seismic reflection data that were acquired in Shibugamo by the Metal Earth project in 2017. So this data has been published by collaborators, and we have also a paper in Tectonics to wrap it up as and to figure out how this data help us constraining the geodynamic evolution of the area. We also had several masters and students working on this, on the field data and on this any data we collected here. So, for example, Adrien Boucher worked on the main lava flow formation, the Chibougamau formation, and it gives us insight on the source and dynamism and why this area is not very prospective for VMS. Pierre Bedeau did a lot of work on the structure and is currently working on the sedimentary units on the detrital zircon to constrain the age and evolution of the main sedimentary basins, which are quite thick in Chibougamau for some reason. So this is a work is completing at the moment. And we still have some work pending on the empty data. That's a collaboration with Ademola. With Jeff Harris, we are also working on the prospectivity model. This is a paper in preparation. And the last team's UPB age that haven't been published in other papers, we are going to publish them in a single paper with Mike Hamilton. Actually, I've made a mistake here. Mike Hamilton will probably be a first author on this. So this is the main work we did, and to conclude on this, it really changed a lot of things for the Chibougamau area. We now have a nicely wrapped geological model for this area. We connected it to the metallogenic evolution of the area, and we understand better its volcanic, magmatic evolution and its structure. And when the data on the detrital zircon will be published, there will be also more a complete new view on these sedimentary basins that haven't been worked much in the past. So it really changes a lot for this area. Now, what was really interesting to do with this work on the Chibougamau area was to start looking around to see how it fits in the Abitibi greenstone belt and how it compares to the rest of the greenstone belt and to other greenstone belt. So one of the things we did recently, and that was a great success, there were several groups in as part of Metal Earth who published papers in this special issue of GSA. It's a series of papers on turning points in the North American craton. So these papers with the one with the figure here, it's a review of geodynamic models that may apply to the superior province. And we had other papers on different thematics. So this will give, I wanted to mention it because this will give a lot of visibility to the Metal Earth project. This is probably going to have a large audience. So this is one of the things we did with the data we acquired in Shibugamo and how we implemented them, compare them to the rest of the superior craton. This is an example of a reflection, some ideas on geodynamic models. In these papers, again, we summarized, we review a lot of models and we conclude on or preferred model for the evolution of greenstone belt, which involve older craton nuclei and rifting to make room for the greenstone belt. This is also what was proposed in another paper for the Matagami Shibugamo greenstone belt. So it doesn't mean subduction is impossible. There's probably part where the subduction were active, possibly starting in the new Archean. But for places like the Shibugamo and maybe most of the greenstone belt, a rifting of an older craton nuclei can give you the start of the initiation of the development of your belt. It actually works with the data that we have. So this is summarized in this contribution. Okay, so for the rest of the presentation, I'm going to focus on the magmatic system and on all the insight we gained on this as part of this project. Just to tell you, we focused on intermediate to felsic magmatism, but we also had side project on this mafic magmatism, which produce this large layered intrusion in Chibougamau. The layered intrusion is called the lac doré complex, and it is important because there's a lot of exploration for vanadium, vanadiferous titanomagnetite in this area. So vanadium is an important metal, especially with the energy, the transition at the moment. So this was, it was a bit of metals project. It was mostly a FRQNT project, but I'm putting it out there just to show you that we really looked at every geological entities in the Shibugamo area. So why is there a layered intrusion here? There is another one in the Matagami Shibugamo greenstone belt, so it seems to be a favorable area for that kind of magmatism. And the result of this project was to study the magmatic evolution of the layered intrusions and to compare to, we mostly focus on this area in the blue and red here. It's called the layer zones at the iron enriched unit in the lac doré complex. And we looked along this unit to understand how it formed and why part of it are mineralized and other part are not. So these are projects which have a lot of implication for local exploration projects. There was also a master project by Amadou Youssoufou, who worked on the soda granophyre at the uppermost unit of the lac doré complex, whose origin was very controversial. So he did a great job finding out how this unit formed, so mostly by fractional crystallization and possibly contamination. And this has implication for our understanding of the volcanic and magmatic evolution of the last stage of volcanic cycle 1. This is all that you need to know about that, is that it's a time where VMS formed in the Shibugamo area. There's only a short window in Chibougamau when VMS formed. So this project had implication for our understanding of the volcanic and magmatic architecture at this time. Moving on to the magmatic system, the main intrusion of the Shibugamo area is called the Shibugamo pluton, and it is important because it is associated with copper-gold porphyry style of mineralization in central camp, south of the Shibugamo city, and with other copper-gold style of mineralization in the pluton and outside of it. So this pluton, the main question we had is why was this magmatic intrusion able to contribute fluid to a porphyry style of mineralization, which is a style of mineralization that is very unusual in greenstone belt. So among the main results, there's been a lot of work on the petrography and chemistry of the intrusive phases, and early work and early compilation of the data by Denis Rassico shows that there was 2 main intrusive phases. And this is something we are refining at the moment with Alexandre Crépon, who initiated a PhD, but it was interrupted. But at least there will be a paper coming out of that. I'm completing it at the moment. And you will see much more detail on the petrogenesis of the intrusion, a lot more data on the age. And it's really surprising. We have a range of ages, but mostly two main intrusive phase, a symvolcanic one and a syntectonic one. And we can see the source is completely different in this both intrusive phase. So one that is important for the mineralization is the early one, the diorite-dominated intrusive phase. So diorite are paramount to the mineralizing process here, as it's seen elsewhere. Like Côté Gold is also related to a diorite-dominated intrusion. If you go north of the Abitibi greenstone belt, you go to Troilus, same story. So this tells us that diorite are very important for this style of mineralization. We've also done work on the chemistry of pyrite, because it can tell us a lot about the type of fluids that circulate in the area. And I'm completing another study with Denis Saval here at UQuac at the moment, using a new generation of laser. And we've tried to map a few of the pyrite here, and just with 1 or 2 samples, you can figure out the bulk of metallogenic processes that have been deduced from field data in this area. So it's quite promising. And also with Dan Contact, we have results on work on fluid inclusions that confirm that the fluid that circulated in this area are the magmatic origins. They compare to what we see in other porphyry systems. So I have no more restraint. I'm going to call this a porphyry style of mineralization, no matter what. It has all the characteristics of that type of mineralization. There is another diorite-bearing intrusive system in the Shibugamo area. That's the second largest intrusion in the area, and it's called the ozone complex. So because of its chemistry and because of its size, we decided to have a master project on it. So that was Marie Kiefer, who did a great project on this intrusion. She published the result of her master already, and there is another paper coming in collaboration with the Laval University, referring a lot to oxygen isotopes in the vein system in one of the molybdenum showing located inside the intrusive complex. So the initial work of Marie Kiefer show what we see also in the Shibugamo pluton. It describes all the characteristics of these diorite phases, which tend to have limited to a very moderate heavy earth element depletion and other chemical characteristics that tell us there is a strong mantle component in the source to this magma. Just to move north, I was talking about Troilus earlier on, and here you have another project. So Troilus is here. There is another project nearby called Regno, and recently I looked at the diorite intrusive rock in this area as well. So and we see similarities in the chemistry and petrography between the diorite of different places. So one thing that's one type of intrusion that is very interesting also for exploration, and its petrogenesis. We now understand it better, but there's still things to be done to constrain it properly. So looking at how all of this fit in the rest of the Abitibi greenstone belt, I will start with this diagram. This is a work we did a few years back, and it's a compilation of intrusive rock, of the chemistry of intrusive rocks from the whole Abitibi greenstone belt. And these intermediate to felsic intrusive rocks can be classified into two main groups, the TTG intrusive suite and the TTD intrusive suite. So TTGs, they have the typical characteristics that are known for TTG, this heavy earth element depletion, which is due to garnet at the source. The source of this magma is a hydrated, enriched, and metamorphosed basalt. And you've got the color code here is the silica content, and you see that as differentiation progresses, there is less and less trace element in the residual melt. Everything is different for TTD suite, and I'm not going to go through the whole story, but the idea is that there is a mantle component at the source of TTD suite. Probably not a simple mantle component. There could be metasomatism by TTG melt at this source. There is some chemical indication of that, but it's still different sources. They are coeval, but they don't have the same source, so they are not the same type of magmas. Having a mantle component at the source is probably what is important to generate melt, to generate the TTD suite, and to generate melts that are able to exsolve copper gold bearing mineralizing fluids that can then participate to porphyry style of mineralization. We don't know much or almost none magmatic geothermal system associated with TTGs. If we look at it in a map, this is a distribution here. So the TTG are in red, also in orange and blue. This can be considered TTG. And you see that they represent the majority of intrusive system in the Abitibi greenstone belt. And if we look for TTD, well, we have the Shibugamo pluton here, the ozone complex I was talking about earlier, a few others, and the Chester intrusion associated with the Cote Gold mineralization. You've got Borlamac here. So just a few of them in purple on this map, but not many. So TTD, because they are quite rare, they could be it could be easy to just focus on the look for each of those and explore for each of those just to check if there is copper gold porphyry style of mineralization nearby. They are an interesting type of intrusion to consider for that type of exploration. A bit more, we initiated project on TTG suite as well. The motivation for that is that TTG, well, they are very abundant and they can tell you a lot about the geodynamic evolution of a greenstone belt. That has always been the main motivation to work on this type of magma. From previous work, we know there is a diversity of TTG suites. There are TTG and TTGs. Some produce at high pressure, others at lower pressure, with sources that are a bit different from the greenstone belt to the next. So the more we look at this type of intrusive suite, the more detail, the more heterogeneity we see. The Abitibi greenstone belt is no exception. On this map, I've got the intrusion in blue and red. And these are two groups of intrusion that seems to have crystallized amphibole at different temperature. You see it in the titanium anomaly and the niobium over tantalum ratio. They are a bit different between the two groups. So all kind of heterogeneity. The more you look at this magma, the more heterogeneity you see in their source and in the way they evolve, they differentiated in the crust. So this will require years and years of work to really figure out what this, all of this heterogeneity means and how to relate it to the evolution of the crust. We initiated work on the Kenogami complex. For this reason, this unfortunately has been interrupted. The student has accepted another PhD project. There is still a paper in preparation for what he's been doing for the past year. Okay, so for the rest of the talk, we've talked a lot about the syntvolcanic magmatism. Let me go toward syntectonic magmatism in the Abitibi greenstone belt. Just to show you the volume of rock this represents, you've got syntvolcanic intrusion in orange and probably most of the yellow polygons on this map. And in blue, these are the syntectonic intrusions of the Abitibi greenstone belt. So mostly small stock and dikes, but there is also pluton with significant volumes that belong to this syntectonic stage. So it's quite a significant volume of magma for the Abitibi greenstone belt. As I was saying earlier, these intrusions are associated with specific type of mineralization that I compiled last year just to have an idea of the diversity of processes that could operate to produce this kind of mineralization. So this is very preliminary. This is a classification based on physical characteristics of the deposit and also on physico-chemical characteristics when they were available. But this is a classification that is probably meant to evolve in the future. So along this preliminary classification, you've got 5 categories. Magmatic hydrothermal system, so that are the porphyry system I was talking about earlier, that are these are the system of the syntvolcanic stage that produce mostly copper gold or gold copper mineralization. We don't know about molybdenum or significant tungsten mineralization. This is porphyries with copper and or gold. That's the syntvolcanic stage. Then some of these porphyry style of mineralization seem to be strongly overprinted by orogenic gold system, OGS on this slide. So that's also occur in central Kant. You've got minor immobilization of the gold, and there is probably other systems that have these characteristics with more or less overprint. Then you've got the category that is that developed during the syntectonic stage, which is the famous intrusion-related gold system, cyanide associated in some places. So these are this magmatic hydrothermal system associated to the alkaline series or other type of magma like Beischlois sanukitorite. These are gold dominated systems. Then you've got the multi-stage system. So they could be years overprinted by OGS, and it's very hard to figure out which of the system actually brought the gold, maybe both, or maybe one of them was superior to the other. And then you've got OGS that are a bit different than what we expect. Like, for example, there is evidence for oxidized, for the circulation of oxidized fluids. So the link between orogenic gold system and magmatism could be the input of magmatic fluid in some of these systems. The typical OGS is not compiled here, otherwise there would not be enough space on this slide. But if we just focus on the deposits that are summarized here, those that are more or less related to magmatic activity, there is still a significant number of them. So the project we did on Syntectonic Magmatism, they are summarized on this slide. We had several thematic projects, like for example, Patrick Berthotti did his master project on Syntectonic Magmatism and on the comparison between the Abitibi and Wabigoon sub-provinces. There is a paper that has been submitted a few months ago that came out of this work. And this paper compared a few intrusions and look at their physico-chemical parameters and try to figure out why the syntectonic magmatism in the Abitibi seemed to be more fertile than the one in the Wabigoon sub-province. Then we had a few projects dedicated to the Shibugamo area, like Julien Higuet worked on the Chevrillon pluton. There's also a paper in preparation. Baptiste Madon worked on several intrusions of the Shibugamo area, and his mandate during his master was to compile, to review all the methods that were available to estimate the oxygen fugacity, the redox state of this magmatic system. So he did a great job on that. And in the meantime, he was able to characterize these parameters for several intrusions of the Shibugamo area. So this has been published 2 years ago. We also have Taylor, she's working, finishing her master project on one of the thematic projects. So she works on the Douai syenite, south of the Matagami town. And we also had another publication who came out recently on a sub part of this project. And Esther Bou, who is mostly funded by NSERC, who works on Syntectomic Magmatism. And her first paper will be on the Opemiska and Barlow Pluton in the Shibugamo area. And the other papers will extend the classification, will really review the classification of syntectoid for the rest of the Abitibi greenstone belt. Initially, we wanted to think about what is the syntectoid, how can we classify them at the scale of several greenstone belts, but it turns out there is so many local variations that we have to start with the Abitibi greenstone belt. And yes, there's also some work I did on the Muscocho Pluton. It's also located in the Shibugamo area. So in the time that I have left, I will show you why this work on syntectonic magmatism and its physico-chemical parameters is important. First of all, what do I mean by physico-chemical parameters? When you study this intrusion, you're not just interested in the chemistry of their source, in the condition of their partial melting, or on the characteristic of differentiation process, so petrogenesis. Petrogenesis it's important, but it's not the only thing that we are looking at. We are also looking at two main parameters, the oxygen fugacity of this system and their volatile content. Why? It's because we know that these two parameters are paramount in maintaining gold in the magmatic system. So if we want to figure out how much gold this magmatic system were actually able to carry through the crust during the syntectonic stage, we need constraint on this, the oxygen fugacity and the volatile content. There has been experimental work by Bocharnikov, for example, who show who was able to demonstrate which characteristic, which oxygen fugacity was optimal for the transportation of gold in mafic and intermediate systems. So this is what we are looking at. We are measuring oxygen fugacity to see whether we are in this window or not. So of course, as I was saying, there is a lot of work on petrogenesis to be done to give a framework to the intrusion, because an intrusion that then plays too deep in the crust or crystallizes too slowly will never be able to exsolve fluid that will produce an interesting magmatic geothermal system. So all of this classical technique can already tell us whether a system is prospective or not. And then you add the oxygen fugacity parameters on top of this. These are the result of a baptismal master. So you did do that by working on the chemistry of zircon and apatite. Apatite gives you the sulfur content of your melt. And if you add titanite in the mix, you get the access to the fluorine content of the melt. And these are the constraints that we have for the amount. So there is a big review of David Moll from last year, who give us a range of FMQ values. And from the other work, we know that although the symvolcanic intrusions, they tend to have moderate oxidation state around FMQ. And it's not just the anvil, we have measured it in other intrusions now. We now have the data for the Shibugamo Pluton, for example. And when you go to the syntectonic stage, the oxygen fugacity is higher. It's amazing, the Shibugamo Pluton, you're around FMQ or FMQ +1, and you move to the syntectonic stage and you're plus 1.5 or something like that. So it's a tendency that we see in every magmatic system. There is also other advantage of working with zircon. You can have discrimination diagrams, and you can start working on the timing between the zircon crystallization with the associated age and the timing between these and the hydrothermal event. There is an infinity of things you can do with zircon. So I think I'm at the end of my time. So just to conclude, working on the Shibugamo area was amazing to review what are the main magmatic evolution of the greenstone belt, and to see how important it could be for any mineralizing system which are associated with the magmatic activity of an area. And the hope for the future is to be able to wrap all of this up, to characterize as many intrusion as possible, to figure out how copper and gold and other metals were transported through the crust, and which into the system are actually important to fertilize the upper crust in gold, for example. And the hope that we have for the future is that if the magmatic system of the Abitibi greenstone belt has something that is unique, like for example a source that is particularly enriched in gold, or another unique characteristic like oxygen fugacity or volatile content, that could explain part of the gold endowment of the Abitibi greenstone belt. So this is something we are going to figure out in the future by characterizing this magmatic system and comparing them to the magmatic system of other greenstone belts. Thank you very much.
Well, great. Thank you very much, Lucie. Man, you have been busy over the last few years.
I would say.
Yeah, we have time for a question. Okay. Well,
that's okay. I'm ready for lunch.
Wait. I had to find my unmute button. This stick tussle. Thanks, Lucie. That's very, very nice. Lots of work. I agree with Ross. My question is, as you know, I mean, porphyries are upper crustal phenomenon. So it doesn't take long to erode them down to nothing. So do you have any idea of depth of emplacement and how much of the upper crust is missing off the top of your porphyry targets or your intrusion-related copper-gold systems?
Yeah, no, that's a very good question. We have worked on the amphibole to answer this question. So it's not perfect, but it gives us some constraint. We also have field evidence like meteoritic cavities, pegmatite, porphyry dikes as well. So there's a lot of porphyry dikes associated with the Shibugamo pluton. So we know it's the same kind of depth as what we have today, between 1 and 5 kilometers, with probably an average around 2 and 3 kilometer depth. For the intrusion-related gold system, it could be a bit deeper. That we have a lesser amount of constraint because amphibole is usually destroyed, or we don't have the pyroxene anymore. There's all kind of things that makes it harder to estimate the depth of emplacement for this system associated to intrusion-related gold system. But for the TTGs and TTD intrusive suites, especially Chibougamau and other areas that we know very well, it's a few kilometers, like today. So I know it's a preservation issue that has always been the issue with the porphyry model, but I would argue that there's many places in Abitibi where subsurface rocks are preserved, like in the Blake River, we have a very subsurface feature, volcanic feature, which are preserved. So it seems hard, but it's not impossible. We see it in the field in many places. Features from a few kilometers below the surface are preserved in the Abitibi greenstone belt.
Yeah, no, I agree. It's not hard. It's what's driving the preservation. Because as you know, they all, there's a whole curve, and there's not many that are older than late Cretaceous, and so understanding the preservation, which is the post-mineral history, might actually help some rather than just focusing on the magmatism.
Yeah, I agree. With the work we did on geodynamic, one of the things that strike me, and I have no explanation, not much explanation for that, is that the orogenic processes in the Neoarchean are not the one we see today. So it's like the mountain range were probably not as high, so not as eroded, so maybe less uplift. Seems to be less vertical movements associated with this shortening in the Neoarchean compared to what we see today. That could be part of the answer, but I know it's incomplete. That's a big question.
Good. All right. Okay. Well, thank you very much, Lucie, and we appreciate all your work over the years.